we really want to address kind of, so it's very much going beyond group theory in a sense. So I want to really drill into what we mean. So people talk about fusion systems, and probably you've heard a few talks about fusion systems. We've heard a few talks already this week about fusion systems. What is a fusion system? I mean, when you see the definition, it's sometimes not that easy to motivate except by using groups or whatever, but I kind of want to drill into what a fusion system is. What is it the fusion system of? What is the structure which underpins a fusion system? Where do they come from, really? What was the global sort of place in which they might sort of reside? So I want to kind of address that question to understand. Related to that, I want to talk about blocks of finite groups and thinking about them kind of in terms of their fusion system. So we can talk about going from blocks to fusion systems, but maybe we'd like to start with the fusion system of a block and then recover the block in some sense. And then we also, in Radha's, so I should say that this talk will follow on from what Radha said, so there'll be significant overlap with what Radha spoke about, but I will try to go beyond what she said in a few different directions, and one of the directions I want to go beyond what she said is in the direction of Spetses, and these are objects which I'll introduce later on, and were introduced by Mahler in 1993, and these are, I want to think of these as sort of analogous in some sense to fusion systems. The abstraction which takes you from a group to a Spets is sort of analogous to what takes us from a group to a fusion system. So I want to kind of motivate that as well. And the other question that's kind of should be in the back of our minds, as Radha's already spoken about, are these local global counting conjectures and group representation theory, which basically try to extract global information about blocks given only local information, say in terms of a fusion system. So okay, so that's kind of to set the scene in terms of what I'd like to talk about in the next hour or so. So, but what will not change throughout the talk is that L will always be a prime number. So I'm going to use L where Radha used P, for example, and G will always for me be a finite group. Okay. Right. So Ellen did a great job at introducing fusion systems for us yesterday. I forget now what it was, but she gave a very detailed description of what a fusion system is. But I'm gonna sort of omit some of the details, precise details, since Ellen did such a good job when she spoke. So for me, a fusion system is just a pair. So S is a finite L group, or maybe not even a finite L group, just an L group. And F is a category whose objects are the subgroups of this L group S. Can you see the mouse when I move it, by the way? Is that working? Yeah, good, okay. Yeah, so the subgroups of S are the objects of this category, and morphisms in the category are just injective group morphisms between subgroups. Okay, so there are a few more details which I'm going to gloss over there in terms of the precise technical definition of a fusion system, but that should do for us for now, just to get the idea. So a key concept for us in the context of fusion systems is going to be the notion of an F-centric subgroup. So an F-centric subgroup is one which is self-centralizing, and one whose F conjugates are self-centralizing. So F conjugates are just the images of isomorphisms in the category F of P. So that's all subgroups Q which are isomorphic via some homomorphism from P to Q. So I want all of those subgroups, including, of course, the identity isomorphism, which is in here. So all of those subgroups to be self-centralizing. So that's what F-centric means. And the other concept that we need is this notion of aut F of P, which is just the set of all isomorphisms from P to P. So that's obviously a group. Okay, good. So what do we mean by a saturated fusion system? Well, Ellen I think probably didn't go into exactly what that means. She just mentioned, as I'm going to do, that there are some additional axioms which need to be satisfied to ensure saturation of the fusion system. But for me, really, it just means that the homomorphisms in the category, the F homomorphisms, are really just determined by these aut F of P for the centric subgroups. So we can think about the fusion system as being generated, if you like, by F automorphisms of centric subgroups. And this is kind of an abstraction, if you like, of the classic, for those of you who know about it, the classical Alperin or Goldschmidt fusion theorem. Good. So as Ellen also mentioned, there's an archetypal example of a finite group G, where S is a CELO in G, provides us with a fusion system F on its CELO subgroup, where homomorphisms are just given by G conjugation maps. Subgroups, obviously, objects is just the subgroups of S. And this will always be a saturated fusion system. So these axioms are satisfied in that case. And the other thing, obviously, this is a talk on a topology conference, so I should mention that which has also been mentioned, I think, by Ellen, that every saturated fusion system has a classifying space. So this is a generalization, if you like, of the ordinary classifying space of a finite group, P completed. And it's a fact now that we know that every fusion system has an analogous space attached to it, in the sense that if F is the fusion system of a group, then what we recover here is the P completed classifying space of a finite group. Okay, so that's just what a fusion system is, just to remind you. Good. Okay. So now I want to talk about blocks, because I'm coming at fusion systems from the direction of representation theory, really, in this talk. So as above, L is a prime number and G is a finite group, and K is a field of characteristic L, which I'll assume to be algebraically closed. And this is, as Rada said yesterday, that the group algebra KG has a direct sum decomposition into indecomposable two-sided ideals, which we call blocks. Okay, just like this. And then the irreducible characters of G are partitioned then according to this decomposition into irreducible characters which lie in the respective blocks. And the same goes for the irreducible Brauer characters as well. Okay, and as Rada said, if you have the identity in your set of irreducible characters, then the block, we say the block is principal, and there's obviously one block with that property. And there's this whole load of local structure attached to a block. So if you have a block B, then one can attach to it a defect group, which is a unique P subgroup of S, I should say. It's a P subgroup, I didn't mention that there, or L subgroup rather, of G, which is attached to B, unique up to G conjugacy. And also, importantly, a saturated fusion system on S, which is unique up to isomorphism. Okay, and when B is principal, this is, as Rada said, that the fusion system that we recover is exactly the fusion system of the group G we started with on its CELO subgroup. So this should all be a reminder from yesterday. I don't want to spend too much time talking about this now. Okay, and the number of alpha weights of the principal block, as Rada said, is just given by taking a sum over the F-centric subgroups as defined on the previous slide up to isomorphism, and then counting for each of them the number of blocks of trivial defect in the group algebra of the F outer automorphism group of Q, defined to be, which is this object is defined to be the F automorphisms modulo the inner automorphisms. Okay, so this is just a number that one can attach to an arbitrary fusion system or saturated fusion system. And the outcome weight conjecture for the block B simply says that the number of weights should be the number of irreducible Brauer characters of the block. Okay, so this is one of the local global conjectures which I alluded to earlier on, and it's one of the sort of motivating things for us. Okay, so now let's think about some examples. So examples of groups. Every group decomposes as a direct product, not direct product, as into simple groups, into simple factors, and the simple groups will be classified. And a very important family of finite simple groups is, of course, the finite reductive groups. So a connected? You start with a connected reductive linear algebraic group and form the finite reductive group by looking at fixed points with respect to some Frobenius endomorphism. And this is going to be a finite group of Lie type. And I'm going to denote by G star its Langlands dual. What will be particularly important for us today is this Hecker algebra, which one can attach to a finite group of Lie type. In fact, rather to the Wahl group of that finite group of Lie type, which is going to denote by W of G. And this algebra can be realized inside the group, if you like, as the endomorphism algebra of the induced representation from the Borel subgroup of G up to G. Okay, so this is a particular algebra that one can attach to an arbitrary finite reductive group. And from this algebra, one recovers explicitly certain characters of the group called unipotent characters. And this is explained in terms of Julian-Lustig theory, which I don't want to go into too much detail about here. But just to say that these characters can be defined explicitly from the Hecker algebra, at least their degrees can be read off anyway from that algebra. Good. And just to remind you, so what I want to do, as I'll do so shortly, is to describe what the irreducible characters of G are. If you take a group element G, then there's always a Jordan decomposition into the unipotent semi-simple part of G. This is just basic linear algebra. And we're going to be interested in the semi-simple part, which I've denoted by S. So this theorem, which is called Lustig's Jordan decomposition of characters, describes the parameterization of the irreducible characters of a connected reductive of a finite reductive algebraic group, finite reductive group, in terms of what are called Lustig series. And so, how does it work? Well, if you take a linear, if you want to understand yeah, so you take an irreducible character of G, then it will correspond to a unique, it'll lie in one of these so-called Lustig series, which are parameterized by semi-simple elements in the Langlands dual. So SS here means semi-simple, and these Lustig series are in bijection with unipotent characters of the centralizer of the semi-simple element in the Langlands dual. Okay, so we can understand, if you like, the irreducible character G in terms of these Lustig series. So this is what Rada said yesterday about the Wahl groups of Lie type, rather Wahl groups or reflection groups really determining by their Hecker algebras information about the representation theory of the finite group of Lie type. It's kind of this result that kind of says it all there, really. And moreover, we can actually read off the degrees of the characters, the degree of the character G in terms of both the centralizer and the degree of this unipotent character. Okay, so that's kind of an interesting fact that we want to kind of understand perhaps more generally. Right, good. By the way, if there are any questions, please feel free to stop me at any time. Right, okay, so I'm going to talk about, I want to get onto the topology, but I want to motivate sort of involving topology in what I'm talking about from the point of group representation theory, which is why I'm spending a fair bit of time just talking about representation theory or classical representation theory. So, so we talked already about the irreducible characters, but what about the block decomposition of a finite reductive group? Well, there's a theorem which says that the L block partition sorry, yes, that should say G, not U carry G. So the L block partition of G is given in terms of what are called zeta series inside the set of unipotent characters attached to G. Okay, in such a way that the principal L block corresponds to what's called the principal zeta series. So zeta here is a primitive E through infinity. Okay, so that's another sort of classical fact, if you like. And for the principal block, we can explicitly describe the characters inside it in terms of the principal zeta series inside these Lustig series. So what we do is we run over all the semi-simple elements, which are L elements, inside the CELO subgroup S of the group G, up to F conjugacy, where F is the fusion system of G. And for each of those, we look at the corresponding Lustig series and just take the principal zeta series inside there. Okay, so this is the theorem of Caban-Ongoa, which tells us basically how to parameterize irreducible characters inside a particular block, in particular the principal block, which will be the block of particular concern for us today. Okay, so this is a nice fact, and already we're sort of involving the fusion system, something topological, if you like, in the description of the irreducible characters. Okay, so this is very, very explicit. So this is something that you can go away if you have a computer and just calculate. You know, so if you want to know, for example, all the degrees of the irreducible characters in the principal block of a finite group of Lie type, then provided you know the local structure, so you know something about the CELO subgroup and you know something about the types of the centralizers of those elements, then you can and you can basically just calculate the number you want. So in this particular case, where G is a symplectic group over a field of 2 elements, S to be 6 of 2, and L is 3, the Wahl group in that case is just B3, which is a Reith product, C2 Reith S3. Q is I'll take Q to be 2, and E is therefore 2 because it's the order of 2 modulo 3. So in that case, we have the following 5 classes of L elements inside S, each of which have the following types of centralizer, so G213 and so on, which is B3. And then for each of them, the centralizers are readily calculated using things we know about orders of finite subgroups of finite groups of Lie type. The Q prime part is easy to calculate as well, and then you know the unipotent characters because you know there's lots of tables or relevant computer programs which tell you the unipotent characters of centralizers of the centralizers. So this is all very, very calculable, is what I just want to emphasize here. So it's just to give you some concrete idea of what I'm doing. So I said I wanted to kind of go beyond groups, and this is and the context in which I want to do that is by invoking the theory of Spetses. So what is a Spets? So rather than when we take a linear algebraic group in the background, as we've already mentioned, there's this Wahl group, which is a real reflection group. But what if that Wahl group becomes a complex reflection group? What happens then? And this is a question which interested people back in the 90s, famously on the Greek island of Spetses, where there was a conference, which various people who were interested in this were present. So there's a complex reflection group, and we take an animal which normalizes.
Spetses, right? So,
say again?
There was a big coincidence that they were interested in Spetses, and it was at Spetses.
So these things were actually named after the island. Yeah, I should have said that. Good. Anyway, so there's an element of the normalizer of W inside GLV. So W is acting on complex vector space V. And not every, so we have to place some extra restriction on W. We can't take any complex reflection group, but I guess just think most complex reflection groups are what are called special, which means that they behave in a nice way, sort of analogous to the way that the var group of group might behave, for example. And what we want to do is we want to take this W and attach data to it, data which in the case where W is a real reflection group would mean something for groups. And that's essentially what the theory of Spetses is all about. It's about attaching data to this pair, W phi. And so one of the things we can always do is attach a cyclotomic Hecker algebra to it. So it was discovered that back in the 90s in a paper of Brouet-Mallet-Rouquier, I think it was, that you can attach Hecker algebras to complex reflection groups in a way analogous to the way in which one does it for real reflection groups. I think they're just defined in terms of the fundamental group of a what is it, hyperplane complement or something like this. So you can do this, and then once you have the Hecker algebra, then you can define unipotent characters. Okay, so unipotent characters in the way that one would do it before, for ordinary groups. And then if you specialize this this Hecker algebra, which means you replace U by something in terms of what am I saying here? Sorry. Yeah, I'm not quite sure what I'm saying. That's it. Oh yes, that's right. So if you specialize with respect to some variable x, this u, then one obtains actual degrees. So that's what I'm trying to say, that you can produce degrees as if there was an actual group there, and these were unipotent characters of the group, where QW here is the character field of W. And even better than that, there's also a partition of these unipotent characters into what are called Zeta-Harish-Chandra series, so an analogous way to the way in which one does it for groups. So all of these features were noticed back in the 90s for these complex reflection groups. And as I already mentioned, that if you take a var group, then what you recover here is the Ihori-Hecker algebra, var group of a connected reductive group, and G is the relevant finite group. Then you recover exactly what you expect. And moreover, unipotent characters coincide. Yeah, so the degrees of the unipotent characters of the groups can be read off from the unipotent characters defined generically in this manner. Good. Right. So we're in good shape. So the point is that, as I said, we want to generalize. We want to go away from groups and into the world of Spetses. But there's some missing ingredients. Okay. So we have, as I just said, we have these nice unipotent characters. What else did we need when we were looking at Jourdain's decomposition of characters? Well, we also needed some p-local information, right? We needed fusion systems. We needed centralizers of L elements. We needed a p group, right? We needed an actual L group. So these are the kind of missing ingredients, and it's topology really that comes to our rescue at this point, because without topology, we would have no idea how to define these things for Spetses or given this data. And moreover, we want to do it in such a way that we recover, what we expect for groups. So we want to recover the block theory of finite groups of Lie type using topology essentially. So that's the goal. And L-compact groups, as I say, come to the rescue. So what's an L-compact group? You might ask. Well, an L-compact group is a connected, pointed L-complete space with finite, whose loop space has finite mod L cohomology. And they were first considered by Dwyer and Wilkerson, again, back in the 90s. So it's interesting that it was happening at a similar time to the interest in Spetses, I guess. And soon after the definition, it was observed that, as you might expect, from a space which is kind of closely related to compact Lie groups, which is, I guess, where these things were first noted to come from, that there's an analogous notion of a maximal torus, BT, for an L-compact group, and moreover a var group, which is defined in terms of as a case of connected components of the space of all monoid of self-maps of T. And this group here, WX, turns out to be an L-adic reflection group. Again, very nice. And LX can be defined explicitly, again, in terms of the L-compact group as pi2 of T. Okay, so it's very reminiscent already of the theory of compact Lie groups. But I guess there's obviously a lot of information which we haven't yet extracted, if you like. Mm-hmm. Okay, So there's the theorem that we'll need so using this structure is the fact that one can assign to every L compact group X a pair WXLX, which is a ZL reflection group, in a sort of one-to-one manner, right? So the assignment which sends X to WXLX, as I described it above, induces a bijective correspondence between isomorphism classes of connected L compact groups and isomorphism classes of ZL reflection groups. Okay, and that was proven for P odd by these authors, Anderson, Gödel, Merlo, and Viruel, and then for the prime 2 by Anderson and Gödel later on. Okay, so that's the fact that we really want, because it tells us what these L compact groups actually are. Right, so as I say, we want the local structure. So how do we do that? Well, we need to obtain fusion systems from these L compact groups. So let's start with a simply connected L compact group with a var group W. Take a prime power Q and take L different to P, the characteristic of Q. And it was observed by Broto and Muller that in a topological manner, one can extract fusion systems from BX, or using topology, I have to say, in the following way. So what one does is you take homotopy fixed points, right? So you take homotopy fixed points, you have unstable Adams operations corresponding to this psi Q. And when you do that, what you recover is a space which turns out to be, and provably is, the classifying space, as I defined it earlier, of a fusion system, saturated fusion system, on a particular P group S of Q, which again can be read off from the space X in terms of the torus. So, so this is very nice. So not only do we have analogues, if you like, of classifying spaces, we also have analogues of actual fusion systems, so local information, which was not previously available to us without this topological machinery. So, and of course, what one would expect is if one started with an actual compact connected Lie group and produced the associated L compact group, one should obtain the corresponding finite groups of, I should probably have put these two first. One obtains the relevant, the information one would expect if there were an actual group around. So you expect the CELO subgroup, you expect the fusion system, and you also expect, where G of Q is the corresponding finite group of Lie type. And this fact here was actually noted by Friedlander and Quillen quite a while ago. Right. So so this is good. We are generalizing fusion systems of groups of Lie type in a concrete way. Right. And what you might ask, what are these fusion systems? Well, they're exotic systems that we've known about before. So they're associated, for example, to these complex reflection groups of generalized Grassmannian type, which may be exotic, and also famously the Solomon fusion system, which appeared back in the 80s, 90s, probably earlier than that, 70s, in the context of the classification of finite simple groups. Great, so we've obtained some familiar things, and we've got some nice theory now of L compact groups. Great, so what else are we missing? We're missing centralizers. So we need to understand centralizers inside L compact groups. How do we do that? So this was kind of fortunate because centralizers have been considered extensively, it turns out, in the theory of L compact groups in the context of homotopy decompositions. People interested in, like Jesper, in decomposing, classifying spaces of finite groups in terms of centralizers, or spaces in terms of defined terms of centralizers. So that was a fortunate coincidence for us in the context of trying to generalize results from Deligne-Lustig theory. So we start now with a simply connected L compact group with var group W, and observe that to Bx one can actually associate an infinite fusion system F, whose classifying space is X in the following manner. So you can firstly construct a CELO subgroup of Bx, which is given in terms of this infinite discrete P toral group raised to the power of the rank of W, extended by W. So you can form this big infinite group and look at its CELO subgroup, and that will give you the S, and actually build a fusion system on it, which is whose classifying space is X. And what's this F? Well, F is just some embedding of the classifying space of S into X. Okay. So given that that machinery, one can now define centralizers. So if you take an element of S, you want to talk about its centralizer. So its centralizer is defined as the space of connected components of the space of maps in the classifying space of the group generated by X, S, into X. That's what we mean by a centralizer, and that was, I think, defined by Dwyer and Wilkerson back in the day. And this, so this object is connected, first of all, if X is a simply connected L-compact group. And secondly, it's also realizable as a classifying space of the centralizer in this fusion system of S. So that's the first thing that one might like. But we were interested in fixed points. So secondly, if you take S to be an element of the set of bases, a group of fixed points of S under this Q, so this is now a finite L group, then the centralizer in S of the homotopy fixed point space can be realized as the space of homotopy fixed points of the centralizer in the big L compact group, and its type is given by the classifying space of the corresponding fusion system of the centralizer. Okay, so this is kind of what you might expect, but obviously you have to prove all these things, and these things this information can be extracted from. I probably should have attributed this just to people, but it can be extracted from the literature on L compact groups, let's say. And moreover, one would expect that the centralizers one recovers are analogous to the centralizers one obtains in the context of connected, when G is a connected compact Lie group and X is given in terms of G, and indeed that's the case. So the centralizer in SQ of S, so the CELO subgroup of this fusion system is exactly the CELO subgroup of this group, and similarly the fusion system is realized by that group. Okay, so everything works nicely is the point. Right, so now we can go back to the world of representation theory and try to input some of this information and try to actually recover something sensible, some generalization of the block of a finite group, if you like, of Lie type. So our setup is that we take with a ZR reflection group, which is what we call an L-adic Spets. So this is a new notion which doesn't mean much apart from that if you take the C extension of W, then you recover a special complex reflection group. Okay, so we're just taking the L-adic version, if you like, of the Spetses first considered by Brouwer, Mallow, and Michel in their theory. But the good thing about that is that we have access now to both theories. We have access to the theory of Spetses, but we also have access to the theory of L-compact groups via the correspondence between L-compact groups and reflection groups. So we can take the L-compact group associated to W. Now, if you take a prime power P, a prime power Q, whose characteristic is different to L, we can, via the previous slide, attach fusion systems to that data, coming from homotopy fixed points of Bx. And finally, we have these centralizers, which are given, again, homotopically as the space of homotopy fixed points of these centralizer spaces defined for L-compact groups. So we have now all the ingredients, if you like, that we need to produce a principal block, or at least something like a principal block. So we assume that L is odd, Bx is a simply connected L-compact classifying space of an L-compact group, and L is a very good prime. And what we can do is we can associate to the pair GQ, as above, the set of irreducible characters of the principal block, given in terms of the fusion system, the fixed point fusion system. And then what we do is we just run over Lustig series, now defined in terms of complex Hecker algebras, from the theory of Spetses, and take the principal series, as again defined in the theory of Spetses, and obtain something which actually is meaningful in the case where GQ corresponds to a finite group of Lie type. So if GQ corresponds to a finite group of Lie type, then actually the degrees of the characters we get in here, which are defined again by the theory of Spetses, I should have said that, that's the line above, that these principal series inside these Lustig series correspond to unipotent characters of centralizers of L elements, and the degrees are therefore polynomials in X by some suitable specialization as before. And so exactly what one recovers are the degrees of irreducible characters in the principal block of the corresponding finite group of Lie type. Okay, so this is our definition of a principal block of a Spets. So we have this nice definition, and what would we like to do with it? Well, we'd like to investigate particular conjectures which one might like to make about it, which kind of are analogous, if you like, to the conjectures in finite group theory. This is what I mean by the exotic representation theory. We want to kind of do representation theory in this context for this object. So we take G to be a ZL Spets and B to be the principal block as defined above, under the above assumptions. And I guess we can just define the number of what's this? The number of irreducible characters. Is that right, Rada? I've just, my mind's gone blank.
Ordinary irreducible characters.
Ordinary irreducible, yeah. We define that number just to be, again, motivated from results in Gillian literature theory, as Rada explained yesterday, the number of irreducible characters of this W zeta, which he also defined. I guess I didn't define what that means. It's just the corresponding var group of the fixed fusion system, under the action of this Q. So one conjecture one can make, as Rada explained, is that the number of weights, as defined earlier, is equal to this number, right? And that's what Alperin's weight conjecture for Spetses should say. And knowing that would imply the corresponding weight conjecture for groups of D type. So I'm not going to spend much more time talking about that because Rada already did. But hello?
Yes, is there a reason you don't have the twisting here, right? I guess Rada did it with twisting also, so this also works with the twisting, right?
Yeah.
We need to twist. Yeah. Oh, the twisting. Yeah. Right. Sorry. Yeah. We didn't. I did it because.
Sorry. Okay.
Yeah. You can. Yeah. You can. Yeah. I should have. I wanted this. I just simplified things. Sorry.
Yeah. No. Very good. Very good.
It's already complicated enough. Yeah. Anyway. So this is one local global conjecture one can make in the context of these Spetses, but there are others. And again, this invariant on the left here, MSFD, came up yesterday. It's a complicated, again, local sum of count of, I don't know what to say. It's a complicated sum involving numbers of projective and decomposable modules of various subgroups defined in terms of the fusion system. Which again is something that one can extrapolate from statements of Knur and Robinson. So that was the originality of this, and Rada did mention it yesterday. So it's a local invariant, but one can make this conjecture that this particular local invariant, again motivated by what happens for groups, should be the number of ordinary reducible characters of a fixed defect D. So what I mean by that? The defect of a character is just it's given by the power of L, largest power of L dividing the L power of G, largest power of L divided by G, dividing G, and the largest power of L dividing the dividing chi of 1. That's what I mean by the defect of a character. Okay, so so I'm predicting the number of characters of defect D in a block in terms of some local invariant. That's what I'm trying to do. And I've given you a little bit of information about what this actually means. So Q is a centric subgroup here. Sigma is some normal chain of L subgroups in the F out of automorphism Q starting at 1. Mu is an ordinary reducible character of defect D of Q. And these out F Q sigma U mu's are stabilizers inside out F Q of pairs sigma mu. So it's kind of, it's a definition of something which one can actually calculate if one wants to. So we make the conjecture for Spetses, right? Because we have this definition of the principal block B now, that this number should in fact equal the number of defect D, which again, one can make sense of that for this block, characters inside the principal block of B. Okay, so that's a conjecture which is open and would imply the ordinary weight conjecture as stated for groups of D type. Okay, so I just said that, and here are some things we know about it. So we've checked it, for example, for some complex reflection groups, the smallest infinite family, if you like, of complex reflection groups, which are non-trivial. These GRLs, so we do that. We also check it for various fusion systems of a Guade type, coming from the complex reflection groups G29 and G34, which are bad primes. We need to invoke the notion of good prime, which Rada also mentioned yesterday, which was a definition. So these groups here are actually bad for the primes 5 and 7 respectively. And what happens is that we sort of recover some additional Lustig series in the set of irreducible characters of B kind of need to be involved to make this equality true. And that's kind of what one would expect from other groups in this Aguade family. So that was kind of curious because like the fusion system seems to know about something it has no right to know about, at least what might not expect it to know anything about exotic Lustig series in these Hecker algebras. So that was kind of interesting. And also in a paper I wrote a couple of years ago, I didn't realize at the time, but what I'd actually done is checked this conjecture for the Solomon fusion systems, where L2 is also a bad prime. And again, one needs to include additional Lustig series to make this equality true, but only for a couple of defects. Most, only the 2 defects out of infinitely many defects. So it's basically true, except for one slight tweaks, again, which can be realized in terms of the Hecker algebra G24. So we'd like to prove this conjecture, and one approach that we've toyed with is trying to adapt work of Anne, which kind of does something similar for the general linear group. I think it's Day's projective conjecture or something, which is proved in that case, which is very closely related conjecture. So a lot of the combinatorics is somehow already worked out in the literature, and we just need to kind of extract that and work with it like we did for the Alpine wave conjecture, and hopefully we can kind of prove this that way. But that's not, we haven't touched that yet. Okay, so just quickly, because I don't know how much time I have left. I just wanted to go through an example which again illustrates the computability of all of these invariants. So back to the example we had before, where G was SP6 of 2 and L was 3. The var group in this case is just the cyclic group B3, which is C2 with S3. This is the table we had before. And now I've recorded also the defects of the characters, which is obtained by looking at the defect of this character and the defect of this character. I should say the height of this character and the height of this character, and then we work out the defect by taking the difference from 4, which is the defect of S, if you like, height of S. The L power divide, I guess. We'd like to sort of check the ordinary weight conjecture for this example, and in this example, the CELO subgroup is a Reith product. You can check that easily enough. We have to consider, it's enough to consider centric radical subgroups, so it's a slightly smaller class of subgroups for the local count, because it turns out that if you're not radical, then you contribute 0 to the sum. I'm not going to define what radical means now. In this case, there are only 3 subgroups to consider, where T is the torus, which is a C3 cubed, and E is an extra special group of order 3 to the 3. Okay, so each of these subgroups will contribute something to the sum in the previous slide, and here are the numbers you get. So here I'm going to give you a table which gives you the contribution to the sum provided by each of these 3 groups. So S contributes alpha plus 9 because it has characters of defects 3 and 4. It's just an extra special. It's just a Reith product, so we can see that directly. T contributes some number beta, which we don't know, and E, well, I could work it out, but I didn't. And E contributes 1 character of defect 2, and no characters of defect 3. But we know that alpha plus beta is 13, so one can check, right, that the numbers produced by this local count actually do agree. Now, again, this isn't so surprising because this is a group of Lie type, so we expect OWC to be true, but this just illustrates the sort of calculations one would need to do in general to check the ordinary weight conjecture. Good. Okay. So this hopefully will open up a whole kind of new world of potential local global conjectures now for Spetses, where maybe through studying that world we'll kind of get a better understanding of what's going on for groups of Lie type. That's kind of the hope, I suppose. But a different direction one can go in is to actually focus in and hone in on the actual character degrees themselves produced by this definition, and see if we can try to check various arithmetic properties, if you like, of them. So one natural arithmetic number one might want to consider is what the dimension of this principal block is. Right? What is its dimension? Well, how do you define the dimension of the principal block? Well, the dimension of the principal block is just given by summing the squares of the degrees of the characters in it, and so that should be the dimension for Spetses as well, right? We just define it this way, to be a polynomial given by summing the degrees of the characters as defined using the theory of Spetses and L-compact groups. And we might want to ask questions about this number, like what properties does it have? Are there expected properties? Does anything surprising happen? Anyway, so this is the point. So if GQ, for example, corresponds to an actual group of Lie type, then this number here is exactly the dimension of the principal block of G of Q under suitable conditions. And also it's relatively easy to see that for a block, any principal block of any group, the L-adic valuation of the dimension is just given by the size of S. This valuation is the L-adic valuation of S, where S is the CELO subgroup. But in the special situation where we're a group of Lie type, the L prime part of this dimension should be the L prime part congruent to the L prime part of the corresponding Val group, modulo L. So these are 2 properties that one might, which we know for groups, one might expect to be true in this more general context. And actually, we're able to show, and this is again in joint work with Rada and Gunther, that under certain conditions, actually, if someone on the Hecker algebra, this property does hold. But we can't do it in general, although we would like to know this holds in general. We can't prove that in general. We can only prove it under the situation that W is an L prime group, and actually that Q is congruent to 1 mod L, but we expect that condition to be removable with a little bit more work using Springer-Lehrer theory and so on, which Rada mentioned yesterday. So I owe you a definition of strongly symmetric, but it's kind of nice. It's telling us that under something which we hope to be true, strong symmetry of a Hecker algebra, these properties are actually preserved when you pass up to Spetses. So things are still working as they kind of should. So yeah, briefly, I don't want to spend too much time on this definition, but what does strongly symmetric for a Hecker algebra mean? So just to go quickly through things that hopefully people may have seen before. So when we take a complex reflection group and we take its braid group, which is the fundamental group of the space of regular orbits on C to the n, which is the dimension of W. We have a surjection from the braid group to W, whose kernel I'm going to denote by P of W here. And if you once you've formed this braid group, we can what can we do? We can construct a group algebra of it and mod out by what are called the order relations. So this U is just some set of free variables in correspondence with reflections in W. And yeah, this is the way that one constructs the Hecker algebra of complex reflection groups. So various things have been conjectured in the literature about these Hecker algebras of complex reflection groups, and one of them pertains to what are called the Scher elements, which are naturally defined objects attached to irreducible characters in the Hecker algebra. And so once you construct these Scher elements, you can form what's called this particular sum running over characters in H of W, 1 over F chi times chi. And and this is conjectured to be a symmetric algebra. In other words, this T is supposed to be the image of 1 under a HH bimodule isomorphism from H to H star. That's just the definition, classical definition of what it means for an algebra to be symmetric. Okay, right. But we want more than symmetric. We want strongly symmetric, and strongly symmetric means not only are we symmetric, we also have some nice properties. Okay, so properties that one might like to hold, and these properties are given roughly as follows. So this under this section W to W, which is the map back from W to the braid group, the image in H, because the braid group is defining H, is an A basis with this property, that T of HW is delta of W1. And secondly, that T restricts to the parabolic subgroups, right, in a natural way. So we take the symmetrizing form for H, we can pass down to a symmetrizing form for a parabolic subgroup. So these are some technical conditions which just mean that T is nice. Okay, that's all I'm trying to say here. And one can check these conditions, and they've been checked in a number of cases. For example, for complex reflection groups of Grassmannian type, under these conditions, when n is not 2 or r is odd, by Malamata. So these are conditions which one would expect to be true, right? And they're conjectured to be true in many cases. And so this is the condition which we need to guarantee our conjecture. But you might ask, well, what do these conditions have to do with these arithmetic properties of the dimension of the principal block I wrote down before?
What is it? This example of something? Do you know something which is not strongly symmetric, just to get an idea?
I don't know if we do we? Well,
no, we don't. I think we don't need. We don't know any examples.
Yeah. Yeah. So I wanted to just describe briefly what strongly symmetric has to do with these arithmetic conditions on the dimension of the principal block. And this goes via some new algebras which we constructed in our recent paper called Yokonuma algebras. And so these algebras, I'll define them now, seem to be the right way to kind of view or understand these arithmetic conditions in terms of Hecker algebras, at least in nice cases. So we need to assume again that W is an L prime group, that Q is congruent to 1 modulo L. So we have the torus of the L compact group associated to W as before, using the theory of Berto and Muller and so on. And via the action of W, which is a quotient of the braid group actually acts on the torus T. Okay, so that's nice. So given this action, what we can do is we can form the group algebra. So this is like some sort of central extension of the Hecker algebra, right? But with T now sitting underneath. And we can do some analogous construction of the Hecker algebra where we mod out by some different order relations given in terms of elements of T and also the reflections in the braid group of W. So it's a larger algebra, and that's what we mean by the Yokonuma algebra. And these algebras, I think, were considered in the context of knot theory before, and in various other places. So they've been studied before, but they turn out to be of relevance to us here as well. But they weren't ever considered, as far as I know, for ZL reflection groups. I think they were considered, you know, in other contexts. So yeah. But as for Hecker algebras, we can also specialize. So if we take a homomorphism, a Z algebra homomorphism from this ring to ZL, we can specialize Y accordingly, according to so according to some algebra homomorphism defined perhaps in terms of Q. And in this particular case, we recover exactly a slightly larger algebra defined in the case of finite groups. The Yokonuma Hecker algebra is given as the endomorphism algebra of G mod U rather than G mod B, which is what you'd get if you took the Hecker for the Hecker algebra. In the case where G is a finite reductive group. Okay, so this is some enlargement of the Hecker algebra, if you like. Okay, so so what we show is that if H of WU is strongly symmetric, I think, yeah, then in that situation, the specialized Yokonuma Hecker algebra is actually isomorphic to the group algebra. Okay, and it's that fact that allows us to then describe the irreducible characters of B in terms of Schur elements of this algebra, and then also relate properties of the corresponding Schur elements in here and the symmetrizing form in here to the corresponding properties over here. So the divisibility properties we seek essentially follow from this isomorphism, essentially. That's what I'm trying to say. And some results of Isella, Gilleen, Kessler, and Kuhlmann. Okay, so that's kind of what's underpinning the whole proof. Yeah. Hello?
Yes. Okay. What is, like you said, the group algebra? So is that you have a TV? What is? Maybe I lost.
The group algebra. I just mean this thing.
Oh, this thing. Okay.
Yeah. So this is a group, and this is a ring, and
Sorry. What is that? The thing which is in the theorem?
That's this. This is a specialization of that algebra here, with respect to this group homomorphism.
Right. But then your theorem identifies that with just the group ring?
With the group algebra of the torus normalizer, TW, inside the L compact group.
Oh, with torus normalizer. Okay, so that's what this.
That's what TW is. Yeah, I should have said that more clearly. Yeah. Okay, so one interesting question is to try to find a larger algebra, which is analogous to Y in the case where L divides W. So when the L compact group is a more complicated, maybe exotic one or something, what would be the right algebra that would replace Y here, and why does that then allow us to prove these divisibility properties that we're interested in?
Sorry, so a discrete approximation to that, or what do you mean exactly by the group? The group normalizer, the torus normalizer. So T is
so I just mean so in the case where L doesn't divide W, then that's always true. So that the torus normalizer is just given by the product TW, right?
What is T exactly now?
Okay. Yes, I want the finite. So T is the torus of the L compact F of Q. So this is like a homocyclic group.
Right. So you do the discrete approximation.
Discrete approximation, yeah. So this is like exponent L to the A, where L to the A divides Q minus 1 or something like that.
That's right.
Yeah. That's what I mean. Sorry. Yeah. Good. So yeah, we'd like to generalize this to remove this condition, but we don't know how to do that. And I think that would have some really interesting ramifications for groups of Lie type as well. Okay, so I'm almost finished. I just wanted to go talk about some future directions that we hope to kind of go in the future. So one direction which we talked about yesterday after Rada's talk was this theory of L local compact groups. So these are classifying spaces of saturated fusion systems on infinite L groups of the form TS0, where T is a rank R discrete p-toral group, and S0 is some finite group. So these are just finite extensions of these things that look like this. And we have classifications in a number of cases. That's kind of where the interest comes from my perspective, which is that we, together with Bob Oliver and David Craven, I worked on classifying all of these types of saturated fusion systems when the S0 is of order L, And that was extended to a complete classification by Oliver and Ruiz, in the case of discrete L local compact groups. And so these classifications we can use them, and we can ask questions about the behavior of the fusion systems that come out from these classifications. And that's from the representation theory point of view. And that's something I would be interested in doing, studying analogs of Adams operations and homotopy fixed points, which have been defined by people like Alex Gonzalez for L local compact groups. But there is this problem of connectedness, which we alluded to yesterday. We don't know what we mean by a connected L local compact group, or which of the fusion systems that come out from this classification are connected. And that would be something that we would have to address. But maybe studying some of these local global conjectures, as we talked about yesterday, might give some insight into what those conditions could be. And other questions that are like, well, what are the Hecker algebras in this context? So yeah, what do they look like? Do they exist? Questions of that sort, where these var groups can get pretty exotic, and they can be quite, have quite weird representations, which show up in these classifications. So are there Hecker algebras out there which kind of are useful or interesting in this context? And a second direction I just want to touch on briefly is the notion of a non-principal block. So we talked only about principal blocks today, but we have this parameterization of the unipotent characters of a Spets in terms of these zeta series partitions, which work, so it works just as well for Spetses as it works for groups. And so that should correspond to some L local partition of the Spets, right? L block partition. So we should be able to do block theory for other unipotent non-principal blocks for Spetses as well. There's already a Harris-Chandra theory of Spetses, so everything is kind of, all the ingredients are somehow there for us to be able to go off and do that as well. It feels like, anyway. So that's another direction that I think would be interesting to look at. But perhaps one can reduce conjectures about these non-principal unipotent blocks to the principal case. So that's another hope, I suppose, for us. But really, as I said at the beginning, what we really want is a structural reason. So we've dealt with a lot of arithmetic questions, but what's the real structure that's underpinning all of these things? What really is a Spets? Are there analogs of, for example, Deligne-Lustig varieties, which would help us to understand some of the structure that's going on in the background, maybe which can be defined from L compact groups or something. Kind of the questions in the back of my mind to try to understand these things a bit better. But okay, I think I'll stop there. Thanks.
Okay, thank you. Now, yeah, can you hear me? Yeah.
Yep.
Okay. Now you can have you have an opportunity to ask questions to Jason about his talk. Or to ask more questions. No? Okay, so thanks a lot for the talk, Jason. Okay.